So I'll be talking about accelerating real-time analytics with Spark streaming and FPGA as a service. So we have a small crowd here. I know it's towards the end, and I'm assuming all of you guys are FPGA aware, FPGA fans, right? Okay, good. So I'll make this short and sweet. We'll focus on FPGAs, how we use it for Spark streaming. As you know, FPGAs have a sea of gate arrays that you can program for different accelerators, and you can customize it. One of the benefits is you get fixed latency, fixed performance from FPGA, so that's why they make it very attractive. And they've been around for quite some time, and as you know, since you guys are aware of FPGAs, they've been available as PCI cards that you would have to install in your own servers and get it going. What's exciting now is what's changing the scenario. And a game changer is that the leading cloud service providers and leading OEMs are providing these platforms now, standard platforms with FPGAs plugged in. So that's, I think, opening up a real opportunity. So I'll be making the case today of using FPGA for Spark streaming acceleration. So as a brief introduction, I'm PK Gupta. I'm co-founder and CEO of Megh Computing. We are a startup based in Portland, Oregon. And our mission is to enable what we call the third wave of computing in the data center with scale-out deployments of FPGAs. And our founding team is from Intel, so that's why I see some familiar faces here. And we worked on pioneering the use case of FPGAs in the data center and worked on some exciting products, including the first Xeon plus FPGA integrated products. So now we are talking about Spark streaming. So as a brief overview of the talk, I'll start off by talking about Spark streaming use cases, focusing mostly on the real-time use cases, and you'll see what's driving those use cases. We'll talk about FPGAs, why FPGAs are ideal for those use cases, especially in its capability to deliver low latency and high throughput in the applications. And then the two attributes I'll talk about, inline processing and offload processing, and I'll explain those more as I go into the presentation. There are some challenges in using FPGAs in the data center specifically, as I'm sure you're aware of, and I'll talk about how a platform addresses those challenges by hiding the complexity of the FPGA and making it transparent to the application. So there are two key components on the platform, the runtime and the accelerator function units that I'll discuss briefly, and then finally conclude with some demo applications and show some performance on a platform that we're getting today. So diving into it, Spark streaming with machine learning and deep learning for real-time analytics is gaining wide-scale adoption, right? And there's a recent study I saw, very recent, that said that just the streaming analytics market itself is going to be about 16 billion in a few years, in 4 or 5 years, right? Growing at over 30% CAGR. And what's driving it is the different use cases for streaming analytics, including some well-known use cases in the financial world for risk analysis, risk mitigation, fraud detection, in the sales and marketing world in terms of customer interactions and doing in-time market promotions. In the operational world, getting operational insights from data coming in, and a host of other use cases, including for intelligence community and other applications. And what's driving it is the explosion of data, as we are showing here on the left-hand side, the explosion of streaming data generated by various sources, whether it be IoT sensors or events, web data, web applications, social media data, and operational data. So all these data coming in is driving the need to process this data in real time. So as we know, the data analytics can be done in either batch mode or real-time mode. This graph is showing the value of the data decaying with time. So the business value of the data is higher, obviously, if you process it sooner than later. In typical batch mode, we are processing the data in delays of minutes or hours or even days. And that's your traditional batch intelligence that you get from the data. It's like looking in a rearview mirror because the data is old, while trying to guess the performance for the business going forward. Our focus is on the real time shown on the left-hand side, where you can get actionable insights from the data as it's streaming in and make time-critical decisions on the data. So I'll focus on some real-time use cases that's driving, that's motivating us to build the solution. So on this graph, we show from left to right the increasing need for real time. So on the extreme left is shown what is you could call hard real time or real time, where systems need to respond within picoseconds or microsecond, and those are typically implemented as special systems, special hardware and software systems. And so that's outside of the scope of the solution we are talking about today. But everything you see on the right of that, the exciting news is that that can be done today using standard platforms deployed in either the public cloud or the private cloud, using FPGAs, and then using standard frameworks like Spark streaming. And so to look at some of those use cases, regular trading typically has requirements of response time in tens of microseconds. So here you have financial firms that might be looking at market data and then making portfolio and balancing portfolios based on risk assessment and making that available to their customers too. I'm calling this regular trading as opposed to high frequency trading, which is a small niche market more on the left side, where it typically requires custom platform. And then you have the use cases for fraud prevention, which typically response times based on established SLAs in the order of milliseconds or so. And here e-commerce companies might be looking for patterns of misuse or to make decisions on credit card approvals or disapprovals in response time to the order of milliseconds. And then there's a whole emerging use case for edge computing. And edge computing is driven by the need to have decisions in real time, so very low latency, and also to process the data at the edge, so you cut down the data that has to be transferred to the central cloud. And edge computing use cases include IoT devices, it includes AR, VR, and includes like video surveillance, and all those kind of use cases that are typically deployed on the intelligent edge requires response time to the order of tens of milliseconds, typically less than 50 milliseconds. And then you have your regular dashboards that need real-time updates of data, typically requiring response times of the order of hundreds of milliseconds, and that could mean taking real-time data in and doing some real-time inferencing of that and updating that. And then you have your typical operational insights that you could tolerate response times of seconds or more. So we'll focus on the use cases that are driving the real-time needs. So the ability to process all this data coming in and be able to analyze the data and make decisions and convey those decisions in real time is driving the need for very low latency platforms. And then the volume and velocity and the variety of data that's exploding, the need to process that in real time is driving the need for more computational efficient platforms. So the combination of this is driving the need for a platform that can deliver lower latency and higher throughputs. So software-only platforms that are use-only software solutions don't meet the needs for real-time processing. In fact, there are many use cases as the load on a software-only solution increases, the response time actually varies and gets worse, right? Now, if you add an FPGA to that and create a heterogeneous CPU plus FPGA platform, we can guarantee fixed latency times and high throughput. And so that's the motivation for proposing a heterogeneous CPU plus FPGA platform. And these platforms, since we talked about earlier, use standard hardware and standard software architectures. They can be deployed either in the public cloud, the private cloud, or even on the edge cloud, right? As we're seeing more deployments moving to the edge cloud. And as also Microsoft was talking yesterday, I think in one of the keynotes, about the intelligent edge combined with the intelligent cloud. So we're seeing increasing demand for these kind of use cases. And generically, these platforms have to support two properties. One is for inline processing that I'll talk about, and the other one is for offload processing. So here's an example of using a heterogeneous CPU FPGA platform for inline processing. So we are looking at an application here, a general application that has data streaming in on the left-hand side as a standard platform, data streaming in through the system NIC, showing up as RDDs into the executor nodes, and they assume that there's some filtering going on, some transformation going on in the data. Those have to be done as specific tasks, and then maybe we are doing some kind of a ML library function to get some inference data from the information. So this diagram on the left is your standard software-only implementation, and as we increase the data rate and as we increase the load on the platform, the performance typically degrades. On the right-hand side is shown the configuration of using the same application, no changes, but running on a heterogeneous CPU plus FPGA platform. So here the data is coming straight into the FPGA NIC. So we bring the data straight into the FPGA NIC. We process the data, including the protocol of the line protocols, and then we implement the custom filters or transformations on the data on the FPGA itself. And these filters can be programmed and dynamically chained together under software control based on the function required. And then the output from the FPGA is made available to the application, to the executed node, as a standard RDD or DStream interface. So the applications can run unmodified, and they get the data from the FPGA instead of getting it through the other task. And then the application can call the MLIDL function, and so in net effect, by offloading the front-end processing to the FPGA, you get much higher performance. So this shows in more detail how we do the inline processing on the FPGA. So one of the attributes of the FPGA, besides having a sea of gates that we talked about, is they have on-chip PHY and NIC interfaces. So FPGAs can sync in data. Today, the FPGA that we're using can sync in data rates up to 40G line rates. And the next one that we plan to use very soon can sync in line rates of up to 100G. So you're going to have 100G of data coming straight to the FPGA. And then I'm showing the different engines on the FPGA that processes data in real time. So we have a front-end packet processing engine that looks at the data coming in and does a packet classification, and based on the header, breaks the data up into different streams. The data I'm showing coming in can be in different formats, shown in different colors. So it could be audio, video, or text data coming in different formats. And the data through the different lanes are fed through these filters that are configurable and sequenced through under software control. So this is where we implement the transformations for the data needed. And then we finally have a streaming engine towards the end that combines all the data, aggregates the data, and then makes it available into the CPU memory, where the application then can pick it up as a regular RDD stream. So this combination of doing the filtering front end in the FPGA and processing data results in very high performance. So I'm going to show you two examples here. So one on the left is showing an example where there's a 10G line rate of data coming in, and is being processed to look for some change in the data patterns. And the high bar is for a software Spark streaming application in software, and the right one is the lower latency one is for the same application running on the FPGA. And you can see that there's a 10x improvement in lower latency. Now the Spark streaming, I should mention, latency is basically governed by the size of the micro batches, right? Which is typically about 500 milliseconds today. You can go lower, but then you run into the Spark scheduling overheads. Now with structured streaming just coming out, we're very excited to see that. We should be able to do real-time event processing with that, but there's still value in the FPGA because if your data has to be transformed in a certain way before it's processed by the application, all that can be done on the FPGA at line rates, effectively giving you very high performance. And the right-hand side, we are showing an application that's doing a word count. So it's a word count streaming application. And again, you see the difference in performance since the FPGA can sync the whole line rate 10G and do the processing all offloaded into the FPGA, you get 20x higher throughput with the FPGA implementation compared to Spark, streaming and software. And again, these performance numbers, latency numbers, and throughput numbers, since you're implementing it in hardware in the FPGA, you get a fixed performance that doesn't degrade as you increase your load. It scales very well with multiple FPGAs. So that was the application, the example we talked about inline streaming. And next I'll talk about doing offload processing using the same heterogeneous CPU plus FPGA platform to get higher compute efficiencies. So here we are showing an example on the left-hand side on an application that has multiple tasks. Maybe it's doing a DL library function, followed by some SQL queries into the inference that was derived from the deep learning library. And your left-hand side is a standard executor running on a worker node where these tasks are launched. On the right-hand side, we show offloading the DL library function to the FPGA to get much higher performance. And again, the data is from the FPGA is transferred back to memory in a shared buffer as an RDD, and then the executor can pick that up and do the subsequent task without changes. Now, the FPGA has certain attributes that make this offloading very attractive. So besides the sea of gates I talked about, which is the key attribute of the FPGA, and the routing that enables us to connect this FPGAs to map any software algorithm to the FPGA, FPGAs also have what's called block RAM or on-chip memory. So the current FPGA generations and the future coming up have tens of megabytes of on-chip memory. Now this on-chip memory is distributed, so you can now connect your processing elements with the memory very closely, resulting in very high throughput memory bandwidth. Memory bandwidth of the order of hundreds of terabytes per second you can achieve on the FPGA. So combination of the custom processing elements with the very high memory bandwidth and the combination of DSP engines that are also there on the FPGA deliver you very high performance. And again, since FPGAs are programmable and flexible, we can implement custom pipelines in the FPGA. So deep learning algorithms, as they're evolving and migrating towards lower precision weights and the ability to take advantage of sparse DNN matrices, all those map very well to FPGAs. So that results in very well-known performance for deep learning algorithms on FPGAs. So results we've shown show typically you get 10x lower latencies, especially for small batch sizes. So if you're doing like a single image, you want to do real-time streaming application where you're getting data in, you want to process that in real time, you get 10x lower latency and at least 5x higher throughput using the FPGA for ML and DL performance. So all that's the good use case, making FPGAs very attractive, but there's a but. Using FPGAs is quite challenging in the data center. And here I've kind of summarized the three main challenges. One is programming the FPGAs is still difficult. There are some high-level language supports available, but for the most efficient implementations and performance, typically you have to program in a high-level, in a hardware description language like VHDL or Verilog. And then managing the FPGA in the data center so that you can program them, manage them, load the right bit streams in the FPGAs is also complicated and requires some special solutions. And then transparently integrating the FPGAs in the application so applications don't change and can take advantage of the FPGA is also another challenge that has to be overcome. So what we've done as part of a solution is we are offering a solution where we abstract the complexity of the FPGA and make the accelerators shown on the right-hand side in the green box as accelerator function units. We implement optimized versions of the libraries and then expose it through our runtime transparently to the application. So this is a standard Spark configuration that you're familiar with the driver code and the executor codes. We are able to plug in the FPGAs underneath that and get the benefits of the FPGA acceleration without changes to the application. So I'll talk about our platform in some more detail and the main attributes of the platform. So drilling down into our platform, we have two main components in the platform shown in red here. So those are the Megh components. We have an Arca runtime, and the Arca runtime basically supports three features: the management of the FPGA. We have a neat feature called software fallback that I'll explain. And we also, it exposes the accelerators as a service to the application. And then we have the accelerators themselves. We call them the Sierra accelerators, the AFUs, that implement the different functions on the FPGA. And this platform, as shown here, supports both the capabilities for inline streaming and offload processing that I discussed earlier. And these components are available as libraries that get installed in the standard servers and with FPGA cards in them. So they're transparent to the application. So here we are showing first the Arca runtime. So the Arca runtime is shown the different layers in that. Basically, the main function of the Arca runtime is to expose the accelerator as a service to the Spark application. And it offers the accelerator as an abstraction. So the accelerators show up as a high-level API, and we support all the high-level languages, either as C API or C++ or Python or Java or Scala. So we have a runtime that exposes these accelerators under any of those, whatever your programming language is for the application. The runtime also supports the platform capabilities for sharing the data and signaling the data with the FPGA. So we have a shared memory concept where that's shared by the different layers, whether it be the JNI layer or the higher levels. They all have access to the same shared buffer, so there's no duplication and copying of buffers. And we offer a very low latency signaling mechanism for the accelerators to communicate with the application when the data is ready. And the third feature that the runtime provides is the software, the management, the resource management at the node level. So we're assuming a typical Spark configuration where you have a yarn or something scheduler that's kind of scheduling these nodes, but at the node level, the runtime manages the FPGA resources. So, for example, if you have multiple tasks running on the node and they're all contending for the same accelerator, and there are no resources available on the FPGA, then the runtime will switch to a software fallback. So we have this feature where if there are no resources, the task doesn't get blocked, but it runs in gracefully it degrades and runs in software-only mode. If the hardware accelerator is available, we could have multiple FPGAs on a single node, and the runtime will manage the allocation of the FPGA to the application. And then for the accelerators themselves, the Sierra accelerators, we provide accelerators for both for the inline processing and the offload processing. So here we are showing the accelerators, the packet processing filters, and streaming processor that are available as part of the accelerators for inline processing. And the data from the FPGAs, once it's done, so data is coming in, say, through a network interface, is being processed on the FPGA. Once the data is available, it's available to the application directly, and the application then pick up the data as a D stream. So as an example to show how we integrate with the existing applications for inline streaming, here's an example of an application that's doing streaming word count. So that's a standard application on the left-hand side. On the right-hand side, we are showing the two implementations, one the CPU and the second one the FPGA. So these are standard word count functions, and so the CPU implementation goes through setting up the D stream, configuring the IP port on the NIC, and then calling the ETL libraries for the different functions for word count. The FPGA implementation is similar, and so it goes through the same three steps, except in this case, we are setting up the NIC on the FPGA, we are setting up the IP ports on the FPGA, and then the FPGA supports the accelerated version of the functions you see for the split to words and split to sort and split to count on the CPU. And the only change is in a configuration file that makes the task call the FPGA accelerated version if it's available rather than the CPU version. And similarly for offload processing, we provide the accelerators for machine learning, so we have a subset of that, and we are building an optimized library for deep learning that'll be working on the FPGA and should deliver the performance we talked about earlier. And so here, if the DNN library, the topology fits in a single FPGA, in the weights on the FPGA, you get very high performance. But if the DNN topology is such that it needs to use multiple FPGAs, it doesn't fit in a single FPGA, then we support an inter-FPGA network where the topology can be split across the FPGAs to deliver the high performance. And again, the same mechanism before, the runtime supports the transfer of data to the FPGA and the results back to the application. And as an example here, we're showing an application for doing an offload. This is a machine learning library function, k-means. And on the left-hand side, we are showing the standard functions, standard application for k-means. And on the right-hand side, we have two libraries, one the standard MLIDL for k-means, and then an accelerated version of that can be offloaded to the FPGA through the configuration file chain, so the applications can run and can take advantage of the FPGA. So the CPU and FPGA share the same function signature, and so we basically provide transparent acceleration with the FPGA. So these two examples were talking about standard functions, whether it be part of MLLib or ETL-lib, and how we accelerate that on the FPGA. If we were building a custom function, and so this example, I'm going to talk about a custom function, and here we are showing an example of a numAdd, which is a variant of the word count, standard word count, but here it's adding numbers that show up as strings, and the function that we're accelerating is shown in red there, sum1 string, right? So this is the driver code for that. And here we are showing the accelerator operation on the execution node. So this example is showing some of the key attributes of the runtime that we're utilizing to implement this accelerator function. So initially, the first step is to expose the accelerator as a service to the application. And we had the Arca runtime supports an FPGA factory function as a service. So it will either pick up the software version or the FPGA accelerator version based on what's available. If there's an accelerator version available, it's going to pick up that. If not, it'll pick up the software version. So this is how we implement the software fallback. And then we transfer the data into the FPGA using the Arca features for the buffer management. And it's the optimized one, so we have zero copy to hardware with the shared buffer. The data gets to the FPGA, then we signal the FPGA to start. Once the operation is done, the application is able to pick up the data. So this example shows the attributes of the runtime and the accelerator function. And the last slide here, I'm showing the typical profiling results we obtained with the application. And so we're showing the results both for the FPGA offload of this custom application and the performance using the software runtime. As you can see, we get significant orders of magnitude performance improvement as expected by offloading to the FPGA. So in summary, we've talked about heterogeneous CPU FPGA platform that we've optimized for real-time analytics. We have the Arca runtime that supports different streaming frameworks, and the Sierra AFUs that deliver low latency and high throughput for both inline and offload processing. So I think we have time for a few questions, right? Are there any questions?
I have a quick question. So do you see like moving to anything like structured streaming in the future to integrate with FPGAs? Or?
Absolutely.
Okay.
So till recently, we were looking at streaming, just Spark streaming, and the issues we were running into is the micro batch size, right? And so we looked at how we could optimize that, and we were told to use minimum 500 milliseconds. But I know we've seen examples of people who brought that down to below 500, even down to 100 milliseconds. But the problem with going down to that level is that you are running into then the scheduling overhead, and you might not get the benefit of the FPGA. So with structured streaming now that you've just introduced, I think we see it as a great opportunity. So the ability to do inline streaming combined with structured streaming, I think is going to open up a lot more opportunities. I think we can go after applications that need really, really low latencies and also can benefit from offload.
Awesome. Any more questions? Go ahead.
Okay. Were you able to enable FPGA usage by multiply processes at the same time?
For multiple processes?
Yeah. So when you, so for example, if you have multiply FPGA images, yeah.
Oh yes.
So for different purposes, and if is it possible to load them all and use different model for different process that is currently using FPGA?
So if I understand correctly, you're asking if we can support multiple FPGAs and have different applications or accelerators running on those FPGAs?
Yeah, right now. And if it is possible to load multiply images on FPGA, just to share FPGA between different processes.
Yeah. So the first one is what we have today. So the first capability, what we have today as part of the runtime, is we can support multiple FPGAs in the same node, and we can resource manage them across the different tasks running on the same node. So we can do that today. The second part I think you're asking is, can we share a single FPGA across multiple processes? So that is something definitely we are very interested in, but that requires some contextual saving of the process before it can be switched. So it requires some more support from our partners at Intel and others that are enabling the low-level infrastructure, right? But that's definitely something that we see happening soon. Yeah.
Great. Maybe just time for one more question. All the other questions we can take offline with Prabhat.
Have you had a chance to do cost analysis, trying to see like adding FPGA in terms of cost versus using like more CPUs, trying to see like what is the sweet spot, what kind of applications, when it makes sense, when it doesn't make sense?
So if I understand you correctly, just rephrase the question you're asking. If we have
Cost
done
analysis between using
analysis of CPU versus FPGA?
Yes.
Right. So all the data that we are showing, right, is CPU versus FPGA data, right? And we have done, now if you rent, for example, if you're deploying in the cloud and you're renting from the cloud service provider a platform with the CPU and FPGA in it, obviously that is going to cost more than just renting CPUs, right? So we have done the analysis of if you are just running on CPUs only, what would be your total cost versus the performance gains that we are seeing in applications that you could get performance gains at least multiple X, like 2X to 5X. And so that, in the end, the total cost of running the application on CPU for FPGA is much more economical. And so it definitely makes business sense. The ROI is there to run the application on a heterogeneous CPU plus FPGA platform. Absolutely. So that's one thing. That's just like looking at total cost as a metric. The other metric that's important is that there are certain applications with low latency that you cannot achieve on the FPGA, because on the CPU, right? Because you're limited by the CPU processing latencies. With the FPGAs, you can hit those very low latencies, right? So that's the thing. And the other benefit is that with the FPGA and CPU plus FPGA platform, you get known performance. So whatever you profile at, and it scales linearly, right? So as you put in more FPGAs and put in more CPU nodes combinations, the performance will scale. In a software-only solutions, we've seen results where as the load increases, the performance actually degrades.
All right. Let's thank Prabhat again for the talk. Thank you very much.
Thank you.